Welcome, and welcome to our deep dive into the world of forbidden agricultural practices. Today we'll explore 5 controversial methods that, if reconsidered or responsibly managed, could potentially help feed the world. Now, when we hear forbidden, our minds might jump to ancient curses or secret societies, but in agriculture, forbidden often means regulated, restricted, or outright banned due to very real and often very serious concerns. We're talking about practices that have, at one point or another, promised breakthroughs in food production, only to be sidelined by worries about our health, our environment, or the very fabric of our farming communities. It's a complex web of science, ethics, economics, and frankly, fear. The challenge of feeding a global population projected to reach nearly 10 billion by 2050 is, to put it mildly, monumental. We need more food, produced more efficiently and more sustainably. And this is where the tension really mounts, because some of the tools that could dramatically increase yields or make farming possible in harsh conditions are the very ones that carry significant question marks. Are these methods truly Pandora's boxes, best left unopened, or are they misunderstood technologies that, with careful stewardship and updated knowledge, could be part of the solution? It's a conversation that requires us to look beyond simple good or bad labels. So in this video, we're not here to advocate for lifting all bans willy-nilly. Instead, we want to foster a nuanced discussion. We'll examine why these practices were restricted in the first place, what potential they hold, and whether, in the face of global hunger, it's time to re-evaluate our stance on some of them, armed with new science, better regulatory frameworks, and a deeper understanding of the risks and rewards. It's about asking the tough questions and exploring the possibility that some forbidden fruits might, just might, be worth a second look, if handled with extreme care and a profound sense of responsibility. Let's get started. First up on our list are genetically modified organisms, or GMOs. This is a term that, for many, conjures up a whole host of images and emotions, often fueled by passionate debate. At its core, genetic modification in agriculture involves altering a plant's DNA, its fundamental genetic blueprint, to introduce desirable traits. Think of it like very precise, targeted breeding happening at the molecular level. This isn't about cross-pollinating 2 types of apples. In an orchard, this is scientists identifying specific genes responsible for, say, pest resistance or drought tolerance, and inserting them into a crop's genome. The goal, almost invariably, is to create a plant that performs better in some agriculturally significant way. The status of GMOs globally is, to put it mildly, a patchwork quilt of regulations and public opinion. In some parts of the world, like the United States, GMO crops such as corn, soy and cotton are widespread and have been a part of the food system for decades. However, in other regions, most notably many countries within the European Union, there's a much more restrictive approach. These restrictions can range from outright bans on cultivation to stringent labeling requirements and lengthy, complex approval processes. This divergence in policy reflects deep-seated differences in cultural attitudes towards food, technology, and the perceived role of precaution in governance. The potential benefits of GMOs are often cited as a primary driver for their development and a key argument for their wider adoption, especially in the context of global food security. Imagine crops engineered to thrive in arid conditions, opening up vast new tracts of land for farming in regions previously considered inhospitable. Or picture plants that naturally repel devastating pests, reducing the need for chemical sprays and thereby lessening the environmental impact of farming. Furthermore, some GMOs are designed for enhanced nutritional value, like golden rice, which is modified to produce beta-carotene, a precursor to vitamin A, potentially combating deficiency in vulnerable populations. These aren't just minor tweaks. They represent potentially game-changing advancements in our ability to produce more food more reliably. So, if the potential upsides are so significant, why the widespread concern and the stringent bans in many places? Well, the why forbidden part of the equation is multifaceted and deeply felt. One of the most persistent concerns revolves around the potential long-term health effects of consuming GMOs. Critics often ask, what happens when we ingest foods whose genetic makeup has been altered in a lab? While the overwhelming scientific consensus, affirmed by major scientific bodies worldwide, is that currently available GMOs are safe to eat, public skepticism remains high, fueled by a distrust of novel food technologies and, sometimes by studies that, while later debunked, gained significant media traction. Beyond direct health impacts on consumers, there are significant ecological concerns. One major worry is the potential for biodiversity loss. For instance, if herbicide-tolerant GMO crops lead to more widespread use of broad-spectrum herbicides, this could decimate weed populations that serve as food and habitat for insects and other wildlife, leading to a ripple effect through the ecosystem. There's also the fear of gene flow, the transfer of modified genes from GMO crops to their wild relatives through cross-pollination. This could potentially lead to the development of herbicide-resistant superweeds or confer other unintended traits to wild plants, disrupting natural ecological balances in ways that are difficult to predict or control. Another critical point of contention is the issue of corporate control over the food supply. The development of GMO seeds is a complex and expensive endeavor, dominated by a handful of large agrochemical corporations. Farmers who use patented GMO seeds are often bound by strict agreements that may prohibit them from saving seeds from their harvest for future planting, forcing them to purchase new seeds each year. This model raises concerns about farmer autonomy, increased costs for smallholders, particularly in developing countries, and the consolidation of power within the agricultural sector, potentially making food systems more vulnerable and less equitable. The debate around GMOs also touches upon ethical considerations regarding the very act of altering life at its most fundamental level. For some, there's a philosophical or religious objection to playing God with nature's designs. This perspective views the genome as something sacrosanct, not to be tampered with for commercial or even humanitarian ends. While this viewpoint is not universally held, it contributes to the complex tapestry of public opinion and influences the regulatory landscape in regions where such concerns are given significant weight in policy making. It highlights the fact that decisions about food and agriculture are not purely scientific. They are deeply intertwined with cultural values and worldviews. Furthermore, the promise of increased yields from GMOs hasn't always translated uniformly across all contexts. While some GMOs have indeed boosted productivity, critics argue that the benefits are often overstated or are more attributable to associated farming practices rather than the genetic modification itself. They point out that traditional breeding methods, agroecology, and improvements in farm management can also lead to significant yield increases without the perceived risks and corporate dependencies associated with GMOs. This argument suggests that perhaps the focus on GMOs as a silver bullet solution distracts from other potentially more holistic and sustainable approaches to enhancing food security. The regulatory hurdles themselves, while intended to ensure safety, can also be a barrier, particularly for public sector researchers or smaller companies looking to develop GMOs for humanitarian purposes or niche markets. The cost and time involved in navigating the approval process in many countries can be prohibitive, effectively ensuring that only large corporations with deep pockets can bring GMO products to market. This can stifle innovation and limit the development of GMOs tailored to the specific needs of farmers in developing countries, where the potential benefits might be most acutely needed. Ultimately, the story of GMOs is one of immense scientific potential, colliding with profound societal concerns. It's a technology that forces us to confront difficult questions about risk, benefit, control, and the future of our food. Moving forward, any re-evaluation of GMO policies will require not just more research, but also more transparent dialogue, stronger independent oversight, and a commitment to ensuring that the benefits of this technology, if realized, are shared equitably and sustainably, without compromising the health of our planet or its people. Next, let's turn our attention to the use of growth hormones in livestock. This is another practice that sits right at the intersection of agricultural efficiency and public concern. When we talk about growth hormones in this context, we're primarily referring to substances, either natural or synthetic, administered to animals like cattle to make them grow faster or, in the case of dairy cows, produce more milk. The idea is simple: get more product, be it meat or milk, from each animal more quickly. This has obvious implications for the overall food supply and the economics of farming. The global regulatory landscape for livestock growth hormones is, much like with GMOs, quite divided. In the United States, for example, the use of certain growth hormones, such as recombinant bovine somatotropin, RBST, for dairy cows and steroid hormones like estrogen and testosterone for beef cattle, is permitted and has been for many years, following FDA approval. Proponents argue that these hormones are safe, that residues in meat and milk are minimal and fall within natural variation, and that they contribute to a more efficient and affordable food supply. It's a system built on the premise of scientific assessment of risk and economic benefit. Contrast this with the European Union, which has maintained a ban on the use of hormones for growth promotion in meat production since the 1980s and has strict controls on RBST for dairy. This ban extends to imports of meat treated with such hormones, a point of significant trade friction with countries like the United States and Canada. The EU's stance is often attributed to the precautionary principle, which suggests that if there's a credible risk of harm, even without full scientific certainty, protective measures should be taken. This reflects a different weighting of potential risks versus economic gains, and a strong public aversion to what is perceived as unnatural intervention in food production. The potential benefits are primarily economic and relate to production efficiency. For beef cattle, growth hormones can help animals reach market weight more quickly, using less feed per pound of gain. This means a faster turnover for farmers, potentially lower production costs, and in theory, more affordable meat for consumers. In dairy cows, RBST can increase milk production by a significant percentage, again boosting output per animal. In a world grappling with how to feed a growing population, these efficiencies can seem incredibly attractive, promising more food from fewer resources, or at least from the same number of animals. However, the reasons these practices are forbidden or heavily restricted in many regions are compelling and raise serious questions. A primary concern revolves around potential human health risks. While regulatory bodies in countries like the United States assert that hormone residues in treated meat and milk are safe, critics worry about the long-term effects of even low-level exposure to these additional hormones, particularly for vulnerable populations like children. There have been concerns raised about potential links to increased cancer risks, disruptions to human endocrine systems, and the early onset of puberty, though direct causal links remain a subject of ongoing scientific debate and differing interpretations. Animal welfare is another major area of concern. For dairy cows treated with RBST, studies have indicated an increased risk of health problems such as mastitis, an udder infection, lameness, and reproductive issues. This raises ethical questions about subjecting animals to treatments that may compromise their health and well-being for the sake of increased productivity. For beef cattle, while the direct welfare impacts of hormone implants are less clear-cut, the broader system of intensive animal agriculture, of which hormone use is often a part, is frequently criticized for its impact on animal lives. The environmental implications also warrant consideration. While proponents might argue that faster growth and increased efficiency could mean a lower environmental footprint per unit of product, for example, less methane produced over the animal's lifetime if it reaches market weight sooner, critics point to the broader impacts of intensive livestock operations. These systems, often reliant on hormone use, are associated with issues like manure management, water pollution, and the carbon footprint of feed production. The debate here is whether hormones genuinely contribute to a more sustainable system or simply enable a more intensive and potentially more damaging model of agriculture. There's also the argument about the naturalness of food. Many consumers and advocacy groups feel uneasy about the idea of artificially manipulating animal physiology to boost production. This isn't strictly a scientific argument, but it's a powerful cultural one. The desire for food that is perceived as clean, natural, and untampered with drives much of the opposition to practices like hormone use. This sentiment often translates into market demand for hormone-free products, even in countries where hormone use is permitted, indicating a significant segment of the population is willing to pay more for an alternative. Furthermore, the economic benefits are not always straightforward. While hormones might increase output, they can also contribute to market gluts, potentially depressing prices for farmers. Small-scale farmers in particular may find it difficult to compete with larger operations that can leverage technologies like growth hormones to maximize production and lower costs. This can lead to further consolidation in the agricultural sector, with implications for rural communities and food system diversity. The question becomes, efficiency for whom, and at what cost to the broader agricultural landscape? Ultimately, the debate over growth hormones in livestock touches on our fundamental relationship with the animals we raise for food and the kind of food system we want to support. It's a balancing act between the drive for efficiency and abundance and concerns about health, animal welfare, and the integrity of our food. Any re-evaluation of bans or restrictions would need to rigorously address these concerns, ensuring that scientific assessments are robust and independent, and that ethical considerations are given due weight. It's about more than just producing more, it's about producing well. Let's shift our focus now to a practice that is ancient, widespread in certain regions, and deeply controversial slash-and-burn agriculture. Also known as swidden agriculture or shifting cultivation, this method involves cutting down a patch of forest or woodland, allowing the felled vegetation to dry, and then burning it. The resulting ash layer provides a burst of nutrients to the soil, creating a temporary fertile bed for planting crops. After a few seasons, as soil fertility declines and weeds encroach, the farmers move on to a new patch of forest, leaving the old one to regenerate. Ideally, the status of slash and burn is complex. In many countries, particularly those with significant forest cover and concerns about deforestation, it is illegal or heavily discouraged through government policies and conservation efforts. International pressure from environmental organizations and climate change agreements also plays a role in pushing for its cessation. However, it's crucial to understand that for millions of subsistence farmers, particularly in tropical regions of Africa, Southeast Asia, and Latin America, slash and burn is not a choice made lightly, but often a traditional practice and a means of survival in areas with poor soil, limited access to fertilizers, and few economic alternatives. The perceived benefit, especially from the perspective of these subsistence communities, is its simplicity and effectiveness in the short term. It's a relatively quick way to clear land for cultivation without needing heavy machinery or expensive chemical inputs. The fire clears away competing vegetation and pests, and the ash provides a readily available source of nutrients like potassium and phosphorus, essential for crop growth. For small-scale farmers working with marginal lands and minimal resources, this initial boost in fertility can be the difference between a harvest and hunger. It's a system that, when practiced traditionally with long fallow periods, was once relatively sustainable in low population density contexts. However, the reasons slash and burn is so widely condemned and increasingly forbidden are numerous and severe, particularly in today's world of increased population pressure and shrinking forests. The most immediate and visible consequence is deforestation. As more land is cleared for agriculture, vital forest ecosystems are lost. These forests are not just collections of trees, they are biodiversity hotspots, home to countless species of plants and animals, many of which are found nowhere else. Their destruction leads to habitat loss, species extinction, and a tragic decline in the planet's biological richness. Beyond biodiversity, slash and burn agriculture is a significant contributor to greenhouse gas emissions. The burning of vast amounts of biomass releases enormous quantities of carbon dioxide, a primary driver of climate change, directly into the atmosphere. Furthermore, forests are crucial carbon sinks, absorbing carbon dioxide from the atmosphere. When they are cut down and burned, not only is stored carbon released, but their capacity to absorb future emissions is also lost. This creates a double blow for climate mitigation efforts, making slash and burn a major concern on the global environmental stage. Soil degradation is another critical issue. While the initial ash layer provides a temporary nutrient boost, the intense heat from the fires can damage the soil structure and kill beneficial soil microorganisms. Once the initial nutrients are depleted by cropping, the exposed soil is highly vulnerable to erosion by wind and rain, especially on sloped land. This can lead to the loss of precious topsoil, reduced long-term productivity, and in severe cases, desertification, rendering the land unusable for future agriculture or forest regeneration. The cycle of clearing, burning, and abandoning land becomes increasingly unsustainable. The smoke and air pollution generated by large-scale slash-and-burn activities can also have serious public health consequences. Haze from agricultural fires can travel hundreds, even thousands of miles, affecting air quality in neighboring regions and countries. This smoke contains particulate matter and other pollutants that can cause or exacerbate respiratory illnesses, cardiovascular problems, and eye irritation, impacting the health and well-being of millions of people often far removed from the actual burning sites. The economic costs associated with these health impacts and reduced visibility can also be substantial. Moreover, as populations grow and available land shrinks, the traditional model of slash and burn, which relied on long fallow periods, sometimes decades, to allow for forest and soil recovery, is often no longer feasible. Farmers are forced to return to previously cleared plots more quickly before the land has had a chance to fully regenerate. This shortens the cropping cycle, accelerates soil nutrient depletion, and leads to a downward spiral of declining yields and further land degradation, trapping communities in a cycle of poverty and environmental damage. The social and economic dimensions are also complex. While often portrayed as a destructive practice for many indigenous and local communities, slash and burn is deeply intertwined with their culture, traditions, and livelihood strategies. Outright bans without the provision of viable and culturally appropriate alternatives can lead to increased hardship, food insecurity, and conflict over land resources. Finding solutions requires not just condemning the practice, but understanding its socio-economic drivers and working collaboratively with communities to develop more sustainable land use systems. So, when we consider slash and burn, it's a stark example of a practice that, while perhaps sustainable under specific historical and demographic conditions, poses severe environmental threats in the modern world. The challenge isn't just to forbid it, but to support the transition to more sustainable farming methods like agroforestry, conservation agriculture, or improved fallow systems that can provide for local communities while preserving our vital forest ecosystems and mitigating climate change. It's about finding pathways that honor both human needs and planetary health. Our fourth forbidden or heavily restricted farming hack revolves around the use of certain pesticides and herbicides. We're talking about chemical agents designed to protect crops by killing pests, insects, fungi, nematodes, or eliminating weeds that compete for nutrients, water, and sunlight. Think of substances like DDT, which was once hailed as a miracle for pest control, or glyphosate, the active ingredient in many widely used herbicides today. Their primary allure is straightforward: reduce crop losses and thereby boost food output. The status of many pesticides and herbicides is one of constant scrutiny, regulation, and in many cases outright bans or severe restrictions. DDT, for example, is banned for agricultural use worldwide under the Stockholm Convention on Persistent Organic Pollutants, though it's still permitted in some specific cases for disease vector control, like malaria-carrying mosquitoes. Glyphosate, while still widely used in many countries, faces increasing restrictions and bans at local and national levels, particularly in parts of Europe, due to ongoing health and environmental concerns. The regulatory landscape is a dynamic one, constantly evolving as new scientific evidence emerges. The potential benefit and the reason these chemicals were developed and widely adopted in the first place is their effectiveness in controlling threats to crop production. Pests and weeds can decimate harvests, leading to enormous economic losses for farmers and significant reductions in the available food supply. Pesticides and herbicides offer a powerful tool to combat these threats, often resulting in higher yields and more consistent production. In a world striving to maximize food output from limited arable land, the appeal of such a direct and often immediate impact on productivity is undeniable. They can simplify farming operations and, in some cases, make cultivation viable in areas with high pest or weed pressure. However, the why forbidden or why restricted list for many of these chemicals is long and alarming, centered on their impacts on human health and the environment. One of the most significant concerns is the link between certain pesticides and serious human health problems. For example, Organophosphate and carbamate insecticides are known neurotoxins. Chronic exposure, even at low levels, has been linked to developmental problems in children, neurological disorders, and other health issues in agricultural workers and rural communities. Some herbicides, like glyphosate, have been classified by international agencies as probable human carcinogens, sparking intense debate and legal battles. Beyond direct toxicity, the ecological impacts are profound. Many pesticides are not selective, meaning they kill beneficial insects like pollinators, bees, butterflies, and natural pest predators just as effectively as they kill the target pests. This disrupts local ecosystems, can lead to a resurgence of secondary pests, and has devastating consequences for biodiversity. The decline of bee populations, critical for pollinating a vast array of food crops, has been partly attributed to the widespread use of certain classes of insecticides, such as neonicotinoids, leading to restrictions on their use in many regions. Water pollution is another major consequence. Pesticides and herbicides can leach into groundwater or be carried by runoff into rivers, lakes, and oceans. This contamination can harm aquatic life, from fish to amphibians to microorganisms at the base of the food web. It can also render water sources unsafe for drinking or irrigation, creating further problems for human communities and agricultural systems. The persistence of some of these chemicals in the environment means that their effects can be long-lasting and widespread, accumulating in soil and water systems for years, even decades after their application. The development of resistance is also a significant challenge. Just as bacteria can develop resistance to antibiotics, pests and weeds can evolve resistance to the chemicals designed to control them. This pesticide treadmill effect means that farmers may need to apply increasingly higher doses or switch to new, potentially more potent or more expensive chemicals to achieve the same level of control. This not only exacerbates the environmental and health risks, but also increases costs for farmers, creating a cycle of dependency and escalating chemical use. Furthermore, the impact on soil health cannot be overlooked. Many pesticides and herbicides can harm beneficial soil microorganisms, the bacteria, fungi, and other tiny creatures that play a crucial role in nutrient cycling, soil structure, and plant health. By disrupting this delicate soil ecosystem, chemical inputs can, over time, degrade soil fertility and resilience, making crops more dependent on synthetic fertilizers and even more susceptible to pests and diseases, ironically undermining the long-term goals of sustainable agriculture. The socio-economic implications are also noteworthy. While these chemicals can boost yields, the cost of these inputs can be substantial for farmers, particularly smallholders in developing countries. Moreover, exposure risks are often highest for farm workers, who may lack adequate training, protective equipment, or access to healthcare, creating significant occupational health hazards and social equity concerns. The power of large agrochemical companies in promoting and selling these products, sometimes with insufficient regard for local conditions or regulatory capacity, has also been a point of criticism. Rethinking our reliance on these potent chemical tools involves exploring and promoting integrated pest management (IPM) strategies. IPM emphasizes a more holistic approach, using biological controls like introducing natural predators, cultural practices like crop rotation and intercropping, resistant crop varieties, and targeted, judicious use of the least harmful pesticides only when absolutely necessary. It's about working with nature rather than against it to manage pests and weeds in a way that is both effective and sustainable for the long haul. The allure of a quick chemical fix is strong, but the long-term costs often outweigh the short-term gains. Our final controversial practice is the use of reclaimed wastewater for irrigation. This might sound a bit unsettling at first, but in a world where freshwater resources are becoming increasingly scarce, particularly in arid and semi-arid regions, finding alternative water sources for agriculture is not just an option, it's a necessity. Reclaimed wastewater, also known as recycled water, is essentially former municipal or industrial wastewater that has been treated to remove solids and impurities, making it suitable for reuse in various applications, including potentially growing crops. The status of using reclaimed wastewater for irrigation varies significantly across the globe. Some regions, like Israel, parts of Australia, California, and Spain, have embraced water reclamation and reuse as a critical component of their water management strategies, developing advanced treatment technologies and regulatory frameworks to ensure its safe application in agriculture. In these places, it's a well-established practice. However, in many other areas, its use is restricted, heavily regulated with stringent quality standards that can be costly to meet or simply stigmatized due to public perception and health concerns, limiting its widespread adoption despite the pressing need for water. The potential benefit is enormous, especially in the face of climate change, which is exacerbating water scarcity in many agricultural heartlands. Reclaimed wastewater offers a consistent, reliable and locally available water source, largely independent of seasonal rainfall variations or dwindling river flows. This can be a lifeline for farmers in water-stressed environments, allowing them to maintain or even expand agricultural production, enhance food security, and reduce pressure on overexploited freshwater bodies like rivers and aquifers. Furthermore, treated wastewater often contains nutrients like nitrogen and phosphorus, which can reduce the need for synthetic fertilizers, offering an additional agronomic and environmental advantage. So, why the restrictions and the stigma? The primary concerns, understandably, revolve around health risks. Wastewater, even after treatment, can potentially contain residual pathogens, bacteria, viruses, parasites, as well as chemical contaminants like heavy metals, pharmaceuticals, and personal care products that were present in the original sewage or industrial effluent. If these contaminants are not adequately removed or inactivated during the treatment process, they could be absorbed by crops or persist in the soil, posing risks to farm workers who handle the water and to consumers who eat the produce. This is the central fear that drives much of the caution. The level of treatment required is a critical factor. There are different grades of reclaimed water, from primary treated effluent, which is generally unsuitable for irrigation, to tertiary treated water that has undergone advanced filtration and disinfection processes. The cost and complexity of achieving the high treatment levels necessary for safe food crop irrigation can be substantial, potentially putting it out of reach for less developed regions or smaller municipalities, even if the need for water is acute. Ensuring consistent quality control and monitoring of the treated water is also a significant operational challenge. Public perception and social acceptance are huge hurdles. The yuck factor associated with using water that was once sewage is a powerful psychological barrier, even if the water has been treated to a very high standard and is scientifically proven to be safe. Overcoming this stigma requires extensive public education, transparency in operations, and trust in regulatory oversight. Without public buy-in, even the most technologically sound water reclamation projects can face significant opposition, preventing their implementation or limiting the marketability of crops irrigated with reclaimed water. There are also environmental considerations beyond direct human health. The long-term effects of irrigating with reclaimed wastewater on soil health need careful management. While the nutrients can be beneficial, an imbalance or accumulation of certain salts or trace elements over time could degrade soil quality. The specific composition of the wastewater and the characteristics of the soil and crops being irrigated must be carefully matched to avoid negative impacts. This requires ongoing monitoring and adaptive management strategies. Furthermore, the type of crops being irrigated with reclaimed water often dictates the level of restriction. Regulations are typically more stringent for food crops that are eaten raw, like salad greens or fruits, compared to crops that are processed or cooked before consumption, or non-food crops like cotton or fodder. This tiered approach reflects a risk-based management strategy, but it also highlights the complexities involved in setting appropriate standards and ensuring compliance across diverse agricultural systems. The energy footprint of advanced wastewater treatment processes can also be a concern. While reusing water saves the energy that would have been used to pump and treat fresh water from distant sources, the treatment plants themselves, especially those employing technologies like reverse osmosis, can be energy intensive. This means that the overall sustainability of water reclamation needs to consider the energy source used to power the treatment facilities, ideally favoring renewable energy to minimize the carbon footprint. Despite these challenges, the imperative to find sustainable water solutions is driving innovation and a gradual shift in attitudes. As treatment technologies improve, regulatory frameworks become more refined and public awareness grows. The potential for safely using reclaimed wastewater in agriculture is expanding. It's not a silver bullet, and it requires careful planning, robust oversight, and community engagement. but for many parts of the world, it represents a vital piece of the puzzle in ensuring water and food security for the future. It's about transforming a waste product into a valuable resource. So we've journeyed through GMOs, livestock hormones, slash-and-burn agriculture, restricted pesticides, and reclaimed wastewater, 5 distinct farming practices, each with a complex history and a cloud of controversy. As we've seen, these practices aren't inherently evil. They're often banned due to misuse, lack of regulation, or unintended consequences that, at the time of their restrictions, seemed too great to bear. The concerns that led to these prohibitions, be they about human health, animal welfare, environmental degradation, or socio-economic equity, were and often still are very real and very valid. However, the world doesn't stand still. Science evolves, technologies advance, and our understanding of complex systems deepens. With modern technology, stricter controls, and a more nuanced ethical framework, it's possible that some of these methods could be re-evaluated. This isn't about recklessly discarding caution, but about rigorously and responsibly examining whether the balance of risk and reward has shifted, especially in the face of the immense challenge of global hunger and food insecurity. Could some of these tools, if managed with extreme care and foresight, play a role in a sustainable food future? That's the critical question. The path forward requires open-mindedness, robust scientific inquiry independent of vested interests, and a global commitment to ethical and equitable application. It means asking if improved genetic engineering techniques can deliver benefits without the feared downsides, or if advanced water treatment can make wastewater a truly safe resource. It demands that we weigh the immediate needs of a hungry world against the long-term health of our planet and its inhabitants. Would you like to explore alternative, sustainable solutions that avoid these risks but still increase food production? Let us know in the comments below. In